have learned that if a process is carried out at constant volume, then the heat content is the same as the internal energy as no work is done. But most of the chemical reactions are carried out at constant pressure and not at constant volume. When a reaction is performed under constant pressure, then it may involve change in the volume. The energy change occurred during such reactions may not only involve change in internal energy but also do some work. To understand this, assume a chemical reaction occurring at a constant pressure. Let us assume that the reaction is exothermic and also involves gaseous substances. When the reaction proceeds at constant pressure, two possibilities arise. One possibility is that if the reaction is carried out with increase in volume, then the system has to expand against atmospheric pressure and energy is required to perform this act. As some of the energy has to be utilized for this purpose, the heat evolved in this case would be a little less than the heat evolved at constant volume conditions. The other possibility is that if the reaction is carried out with decrease in volume at constant pressure, then the work is done on the system and heat evolved would be greater than the heat evolved at constant volume. Thus, it can be concluded that heat changes occurring at constant pressure and temperature are not only due to change in internal energy but also due to expansion or contraction against the atmospheric pressure. Hence, the scientists felt the need to study the heat changes at constant pressure and temperature. In order to study the heat changes in a chemical reaction at constant temperature and constant pressure, a new thermodynamic function called enthalpy was introduced. The total heat content of a system at constant pressure is equal to the sum of the internal energy and PV. This is called the enthalpy of a system, which is represented by H. Note that enthalpy is also called as heat content. Enthalpy, which depends on the three state functions, internal energy, pressure, and volume, is also a state function. Every substance has a definite value of enthalpy. Like internal energy, enthalpy of a substance cannot be measured. However, it is possible to measure the change in enthalpy. The change in enthalpy is equal to the difference between enthalpy of products and enthalpy of reactants. The change in enthalpy may be expressed as delta H is equal to enthalpy of products, HP, minus enthalpy of reactants, HR. The significance of delta H also follows from the first law of thermodynamics, as delta U is equal to QP minus P delta V. Here, QP represents the heat absorbed by the system and minus P delta V represents the work done by the system. Let U1, U2, V1 and V2 represent the initial and final internal energies and volumes respectively. The above equation can be written as U2 minus U1 equal to QP minus P into V2 minus V1. On rearranging this, we get QP equal to U2 plus PV2 minus U1 plus PV1. But we've already learned that U plus PV equal to enthalpy H. Hence, the equation can be written as QP equal to H2 minus H1 is equal to delta H. Therefore, delta H is equal to QP. For finite changes at constant pressure, we can write the equation as delta H is equal to delta U plus delta PV. Since P is constant, we can write as delta H is equal to delta U plus P delta V. Remember that delta H is equal to QP, the heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions and positive for endothermic reactions. Let's now look at the relation between delta H and delta U. When we deal with solids and liquids, the difference between the change in internal energy, delta U, and enthalpy, delta H, is not significant. This is because solids and liquids do not show significant change in the volume when heated. Thus, if change in volume, delta V, is insignificant, it implies that change in enthalpy, delta H, equals change in internal energy, delta U. The difference between the change in internal energy and enthalpy becomes significant when gases are involved in the reaction. Let's consider a chemical reaction occurring at constant temperature, T, and constant pressure, P. Now, let's say that the volume of the reactants is Va and the number of moles in the reactants is Na. Similarly, the volume of the products is Vb and the number of moles in the product is Nb. We know that according to the ideal gas equation, PV equals nRT. Thus, for the reactants, PVA equals NART, and for the products, PVB equals NBRT. Thus, PVB minus PVA equals NBRT minus NART, or PVB minus VA is equal to NBRT minus NART, or PVB minus VA equal to NB minus NART. That is, pressure P multiplied by change in volume, delta V equals change in number of moles of gas, delta N GRT. Note that delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. We learned that change in enthalpy delta H equals change in internal energy delta U plus product of pressure P and change in volume delta V. On substituting the values, we get change in enthalpy delta H equals change in internal energy delta U plus change in number of moles of gas delta N GRT. This relation helps us in calculating the change in enthalpy from change in internal energy and vice versa. Now let's learn about heat capacity. The capacity to absorb heat energy and store it is known as the heat capacity of a system. The heat absorbed by the system appears as rise in temperature. The increase in temperature is proportional to the heat transferred, which can be written as Q equals coefficient multiplied by change in temperature delta T. Note that the value of the coefficient depends on the size, composition, and nature of the system. The equation can also be written as Q equals C multiplied by delta T, where C is called the heat capacity of the system. If Q calories is the heat absorbed by the system and the temperature rises from T1 to T2, the heat capacity C is given by the expression C equal to Q by T2 minus T1. Thus, heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree at a specified temperature. The specific heat capacity is the quantity of heat required to raise the temperature of unit of mass of a substance by 1 degree Celsius or by 1 Kelvin. Thus, the expression for Q in terms of specific heat capacity becomes Q equals specific heat capacity C multiplied by the mass m multiplied by change in temperature delta T. The molar heat capacity of a substance is defined as the quantity of heat needed to raise the temperature of 1 mole of substance through 1 degree Celsius or 1 Kelvin. The SI unit of molar heat capacity is Joule per degree Kelvin per mole. The molar heat capacity Cm equals heat capacity C divided by N, where N is the amount of the substance. Heat is not a state function, neither is heat capacity. Hence, it is necessary to specify the process by which the temperature is raised by 1 degree. The two important types of molar capacities are molar heat capacity at constant volume and molar heat capacity at constant pressure. Let us see the relation between molar heat capacity at constant volume, which is denoted by Cv, and molar heat capacity at constant pressure, which is denoted by Cp. We learnt that the equation for heat Q is the product of heat capacity and change in temperature delta T. Therefore, at constant volume, heat QV equals product of heat capacity at constant volume Cv and change in temperature delta T. But the heat absorbed at constant volume is equal to change in internal energy. Thus, Cv into delta T can be written as equal to delta U. Similarly, at constant pressure, heat Qp equals product of heat capacity at constant pressure Cp and change in temperature delta T. We have seen that at constant pressure the heat absorbed by the system is equal to the change in enthalpy. Hence, Cp into delta T can be written as equal to delta H. The difference between Cp and Cv for 1 mole of an ideal gas can be derived as follows. The change in enthalpy for 1 mole of an ideal gas can be written as delta H equals delta U plus delta PV. For 1 mole of an ideal gas, PV is equal to RT. Hence, the equation can be written as delta H equals delta U plus delta RT. As R is constant, the equation can also be written as delta H equal to delta U plus R delta T. On substituting the values of delta H and delta U in the equation, we get Cp multiplied by delta T equals Cv multiplied by delta T plus R delta T. Since delta T is equal to 1, we can write the equation as Cp equal to Cv plus R, or Cp minus Cv is equal to R.